chapter 14, simple linear regression. So in linear regression, we have two main objectives. First, we have establish if there is a relationship between two variables. So let me highlight that. So relationship between two variables. Let me make sure the highlighter is good. Looks good. All right. So number two is the forecast new observations. So forecast new observations. So going with number one, sorry I didn't finish. Is there statistically significant relationship? So that's what we want to test also. Is there a significant relationship? So an example that I put was income and spending, wage and gender, and then there's a lot of different examples. So number two, like I said, forecast new observations. Can we use the relationship to forecast new observations on observed values? So the example that I have is, what will our sales be over the next quarter? So that's just an example of forecasting sales. So the variable roles, so our dependent variable is y, and this is the values we want to explain, forecast, or predict. Its values depend on something else. And then we have the independent value or variable x, which this causes the dependent variable. Its values do not depend on anything. So in simple linear regression, we're always going to be dealing with x trying to find y. So y is always going to be our unknown, and that's what we're trying to find. So simple linear regression model, it's called a linear because the equation represents a straight line. So this would be an example of a simple linear regression model over here. And you can see on the right s, r squared and r squared adjusted. That's something that I'll explain later down the video. So here's the formula. I'll highlight that in yellow. So it's y hat equals the capital B O plus B1 times x. And y hat is just a, what's the word again? An estimation. I believe that's the word, yeah. So it's an estimation of y, and so that's why we use y hat. So y hat is the dependent variable just like y. X is the independent variable. Capital BO is our y-intercept. So let me highlight that for you, y-intercept. And that's when x is equal to 0. And then B1 is our slope. So just so you guys remember, BO, y-intercept, B1 equals the slope. So regression terms. Regression analysis is statistically technique that uses observed data to relate the dependent variable to one or more independent variables. We want a regression model to predict the dependent variable based on independent variables. So like I said in the last sentence, it's pretty much using our x values to predict our y values. So BO, capital BO and capital B1, or the y-intercept and slope, are regression parameters. So we must use sample data to estimate them. So we used lowercase bo is an estimate for capital BO, lowercase b1 is an estimate of capital B1. It's pretty much just, it's the same same technique as using y hat instead of y. It's just an estimation, but it means the same thing. So 14.1, finding the least squares point estimate of the slope and y-intercept. So first I'll talk about the slope, and the slope is the first thing that you want to find before finding your y-intercept, because that's going to help you find your y-intercept. So like I said many times, your B1 is your slope, and this is equal to SSXY divided by SSXX. And then, so to find SSXY, I'll put that in green right here. And it's just the sum of x times y minus the sum of x times the sum of y divided by n. So using formula highlighted in green. And to find SSXX, I'll put that in blue. It's just the sum of x squared minus the sum of x, square that, and then divided by n. So just to clarify, this right here the sum of x squared is not the same as this. As you can see that this over here in the light blue, this is the sum of x squared. So you would find all your x's, square them, and then sum them all together. While the one in dark blue is the sum of x and then squaring that. So you would find all your x's and then square it, and just square like that one sum. So hopefully you guys can understand that, because some people make a mistake and just put in the exact same number, but they do mean two different things. So once you find your slope, you can find your y-intercept with the formula of BO is equal to y bar minus B1 times x bar. And to find y bar and x bar, it's here on the right. You could see, so I'll highlight it in orange for y bar. And it's pretty much the sum of y divided by our n, which is the sample size. And then for x, which will be in a yellow, I'll put that, it's pretty much the sum of x divided by n. And then for B1, we find the slope in the first step, which is what I just explained before. And that'll give you your y-intercept. So 14.2, simple coefficients of determination and correlation. So how useful is a particular regression model? Simple coefficient determination is shown by r squared. So our total variation, SST, and this is the total. So our formula, highlighted in yellow right now, is SST is equal to the sum of y minus y bar and to the power of 2. Or it's also equal to SSE plus SSR, and I'll just explain what those are right now. So let me highlight this in yellow. So explained variation, also known as SSR, and the formula, I'll put this in green. And it's SSR is equal to the sum of y bar minus y hat minus y bar, and then square that. So yeah, pretty straightforward. And then unexplained variation, SSE, I'll put that in blue. And it's SSE is equal to the sum of y bar minus BO times sum of y minus B1 times the sum of x times y. So this is a long formula, but it's pretty straightforward, because you could just calculate that in your question, as they'll give you the values of y, they'll give you the values of x, and then you just have to find the sum of that. So the coefficient of determination, like I said, r squared. This is the formula. I'll put this in purple. And I'll just explain this really quickly. So let's say you have your SSE, your unexplained variation, and your explained variation, SSR. You could find your total variation by just doing what I said in yellow, SSE plus SSR. You don't have to do all these calculations here on the left. You just pretty much combine everything together. So the formula for r squared is equal to the explained variation divided by the total variation. So it's pretty much just the proportion of the explained variation. So your SSE divided by your SST. So then the correlation coefficient r, it gives the correlation between y and x. And so if r, there's two formulas. It's not really two different formulas, but either a plus or a minus. So if your B1 is positive, you want to find r, it's just plus the square root of r squared. And if your B1 is negative, it's just to find r, it's negative. I'll highlight that for you in green. So positive, you want to do plus the square root of r squared. And then if it's negative, I'll put that in red, it's minus the square root of r squared. Alright, so 14.3, finding mean square error and standard error. So your sum square error is SSE. What I kind of explained before, it's the difference between the observed value and predicted value. So it's the same formula as above. What color did I put that in? Blue. So I'll highlight it in blue again, so you get familiarized with it. So SSE is just equal to this formula that I explained before. Your mean square error, S squared or MSE, is the average squared difference between observed and predicted values, the point estimate of the residual variance O squared. So your formula, this is a new formula, MSE or S squared. Usually we say S squared, but it is the square or the sum of y minus y hat to the power of 2 divided by n minus 2, or we can also say just SSE divided by n minus 2. So your standard error here represents the average distance that the observed values fall from the regression line, the point estimate of the residual standard deviation O. So your formula is pretty much just S is equal to the square root of S squared. And yeah, that's pretty much simple enough. So 14.4, testing significance of the slope and y-intercept. So a regression model is only useful if there is a significant relationship between x and y, your dependent and independent variable. To test the significance, use HO and HA, your null and alternative hypothesis as your null will be B1 is equal to 0, and then HA will be that B1 is not equal to 0. So an F test for significance of the slope. So your F model here, I'll put that in yellow, is equal to the explained variation divided by the unexplained variation divided by n minus 2. So yeah, and so the first step would be your hypothesis. As I said, B1 is equal to 0. Your HA would be B1 is not equal to 0. Calculate your F test by looking at finding your degrees of freedom. So I'll write that down for you guys. The degrees of freedom. Let me create some space here. So degrees of freedom is equal to n minus 2, and then you have your alpha, which is equal to 1 minus the confidence level. They'll usually give you the alpha anyways, but it's not too hard to calculate it. So the 3 is to reject your hypothesis or accept it. So if your calculated from the F model, if your calculated F score is greater than your F critical, then you can reject your HO. So the F critical is this one right here. So F critical. And then if your p-value is less than A, which is your alpha, you can also reject your HO. Alright, so 14.5, confidence and prediction intervals. So finding your distance value. This measures the distance between XO. XO is pretty much just a number that the question will give you. So just like a random number of X, and then X bar. The further XO is from X bar, the larger the distance. Formula, so I'll put that in, I'll put it in yellow here, and it's D is equal to 1 divided by N plus XO minus X bar to the power of 2 divided by SS XX. And I already showed you guys how to find SS XX on top. X bar, I believe I already showed you. Yeah, right here, just the sum of X divided by N. Okay, where am I now? Yeah, and then your XO is something that the question will give you, so that's where you want to find your distance from. So finding confidence interval and prediction interval. So assume that the regression assumption holds. Confidence level for the mean value of y using the formula. I'll put it in yellow again just because it looks clear. It is equal to the y hat plus or minus your t value times s times the square root of your distance value. And in the prediction interval for a single value, so here it's the, I'll put it in yellow, it's the mean value, and then for your prediction it's for a single value. So it's y hat plus or minus your t score times s times the distance times the square root of the distance formula, or distance value I should say. So in this, your degrees of freedom would be n minus 2. So the formulas are the exact same, but it's the way that the way you interpret it would be different, since one would be the mean value and one would just be a single value. So which to pick? Well, the prediction interval is useful to predict individual values, so individual values. And then the confidence interval is useful to estimate, so I'll put that in yellow, estimate the mean value. So the prediction interval will always be wider than the confidence level, so that's just something to keep in the back of your head while you're calculating either or. And I believe that's it.